Okay, let's get started. All right. So this week we're going to start talking about the Stan language itself. And so now is as good or as bad a time as any to mention that Columbia developed Stan, use Stan, and according to those things that you're expected to make at least $5,000 per year, which I'm not even sure I'm going to do this year. You have to disclose these facts in presentations. So this week, kind of the rest of the semester, we're going to talk about using Stan directly, I suppose you might say, writing your own Stan programs in the Stan language, and then estimating the posterior distribution of them, of the parameters in them. And so this is really the reason why we had to do, a semester of probability and really just a few weeks, so that we would have a few weeks left over at the end of the semester to talk about the Stan language. I guess we'll have one more homework that'll be due the last week of the semester, where we can do one homework involving the Stan language, and hopefully that is enough for you to use it and learn how to use it more effectively on your own. But this basically gives you the ability to estimate almost any model that you could write down mathematically. So how would you do that? First, you write the program in a text file that conventionally ends in a .stan extension. It has R-like syntax, not entirely the same as R, but similar to R. If you actually name your files with a .stan extension, then RStudio will recognize them as Stan programs and does a little bit to format them and highlight the keywords and things like that. Stan's parser, Stan-C, does two things. First, it checks that your program has the right syntax, and it does a reasonably good job. Well, it always tells you if it's not correct. It does a reasonably good job of telling you where the syntax error occurred. And it does these days a very good job of not missing any syntax mistakes or other things like that. It then writes a conceptually equivalent C++ source file to disk. So the Stan program that you write yourself is in a fairly high-level language. It gets translated to fairly low-level C++ that you're usually not even going to bother to look at, but it does get written to the temporary directory. And then the C++ compiler creates a binary file from the C++ source. Now, we started to get into BRM last week, and on the homework, it is basically auto-generating Stan syntax from R syntax, translating that to C++, then compiling that and running it and wrapping it up with the wrapper function BRM and some of the post-estimation stuff. Whereas, once we get beyond BRM, you're sort of doing this yourself. And so when you have some C++ syntax or Stan syntax, say that X is equal to mu plus sigma times Z, which is basically the location scale transformation we've been talking about. The reason why Stan uses C++ is sort of the underlying language for doing computation is C++, more so than other languages, or at least more easily than other languages, can automatically store the derivative of X with respect to mu, with respect to sigma, and with respect to Z, using what's known as overloading of the arithmetic operators in C++. And you can teach the C++ compiler basically to handle the chain rule for you. The chain rule is pretty tedious, but that is the sort of thing that is best offloaded to a computer, because you can basically fully characterize the chain rule in an algorithm, and then the computer does that. It never really messes it up, except in the case where the underlying computation is not particularly numerically accurate. And so this process of basically teaching the C++ compiler the chain rule in calculus, telling it to store the derivatives of these computations as it's going along, is called automatic differentiation. That is a very different thing than numerical differentiation, which is more widely known. That just involves like making a small change to z and then seeing how big a change there is to x in order to calculate the derivative with respect to sigma, let's say. That is very slow, not very numerically precise, but automatic differentiation is basically as precise as the calculation of the derivatives is basically as precise as the calculation of the function values. And moreover, Stan is C++ in combination knows that if one of these things, mu, sigma, or z, is actually a constant, it's observed data, rather than unknowns, which might be the case of z. Z could easily be a constant. Then Stan knows, well, it doesn't need to calculate the derivative with respect to a constant, and so it can save time by skipping that calculation. So that's a little bit of why Stan is using C++ and why the Stan language, which we're going to start to get into this week, has maybe more in common with high-level C++ than it does with R. In event, once the C++ file is compiled into a binary, it's automatically loaded into your R session, and you can execute that from R by calling the Stan function. All of this really can be concurrent with the parser and the compiling and all that. It basically, there's multiple steps behind the scene, but you usually are just calling the Stan function, and then when you get the posterior draws back, you analyze the resulting draws from the posterior distribution in much the same way that we have been doing with RStanArm and BRMS. The difference is, or a difference is, with RStanArm, BRMS, the R side of the computation knows what the model is because it's been sort of programmed by a human in the case of RStanArm, and some combination of Paul and a computer in the case of BRMS. When you just do these things yourself, R has no idea what was going on in the Stan program. It just sort of sent the data off, and it got back this like matrix basically of posterior draws. It has no idea what the model was connecting the data to the draws. And as a result, a lot of the post-estimation functions, even just mapping like what parameter is the coefficient on what x variable, you have to do yourself, because in the R session, it's not known what any of these parameters correspond to. And so doing things like, the Lou information criterion, you have to, in R, give it a function or a matrix that calculates the log likelihood for an individual observation for you, because Lou can't just ask RStanArm or ask BRM, what those values were. So you have to do more work in order to do the posterior predictive checking and all that sort of thing when you're writing these Stan programs yourself. So let's just jump into it. In Stan and C++, and consequently that's the reason why in Stan, variables have to be declared with types. We've seen this already when we started doing a little bit of stuff with the Stan language with functions and things like that. Also in Stan, and because the C++ statements are terminated with semicolons, that basically ends a statement, as opposed to R, where a line break does. Primitive scalar types in the Stan language: real numbers and integers. There are no characters, there are no factors, basically there are no Booleans even yet. Logical variables true and false all there are real numbers. Those have decimal points, and integers, those that don't. And consequently, you cannot have unknown values in the Stan language that are integers, because there's no derivatives of the posterior kernel with respect to an integer. And hence, you can't do Hamiltonian Monte Carlo or the implementation of nuts that Stan uses in that situation. We'll learn maybe a little bit toward the end of the semester how you can sort of get around this problem by defining a slightly different but substantively equivalent posterior distribution that doesn't have integer unknowns. But for now, you can just sort of take it as a rule. Unknowns cannot be integers, but you can condition on integer data because no derivatives are needed for things that are constant and being conditioned on. There's a vector and row vector in the Stan language. Those implicitly are going to contain real numbers. They have to be declared with their size, in this case k, but k would have to be declared beforehand as an integer, because the size of a vector cannot be a real number. It can't even be a real number that is lacking decimal points. It just it has to be declared as integer type. Same thing with matrices. Implicitly, those contain real numbers. They have to be declared with the number of rows and the number of columns. You can have a matrix that has only one column or row, but if you know that you're in that situation, it would be better to use a vector or a row vector, because the computations are going to be more efficient. But it's perfectly acceptable to, like, if you're doing a regression, to declare X as an n by k matrix, and if you're only passing, one predictor to it, it will still work. It should still work even if k is 0, and you're not passing any predictors. Another thing in the Stan language are so-called arrays in the C++ sense, and these are really just holders of homogeneous objects that are more primitive. So you can think of an array in Stan as being like a list in R, with the significant exception that all the elements of that list have to be of the same type and of the same size. In R, a list can hold heterogeneous objects, like it could be, a character vector, a factor, a matrix. Whereas the arrays in Stan, all the elements of the array have to be of the same type and of the same size. So you could declare an array of real numbers by doing real X bracket and then the size of the array. There should be a semicolon after that. And that is very similar conceptually to a vector of size n named X. The difference is that a vector you can do linear algebra stuff with, like pre-multiply it by a matrix, whereas those linear algebra things are not defined for arrays, even if they're arrays of real numbers. And so basically, I've come to the conclusion that if you shouldn't really be declaring a one-dimensional array of real numbers. If you're in that situation, just use a vector, and then you have the option to do linear algebra stuff on that vector or not. Or you could just use it as like a holder of stuff. But there's too much confusion as to, like, should I use a real array or should I use a vector? Always use a vector. But conceptually, these are pretty similar. By the same token, but a little bit more complicated, we can have an array of size k that consists of k vectors of size n. So if we were doing this in R, X would be a list. The list would have k elements in it, and each element would be a vector of n numbers. So this would be like a data frame if all the columns in that data frame were numeric vectors. So again, this is an array. Its name is X. The size of the array is K, the number of elements in that array. Each element in that array is a vector of size n, and this is conceptually similar to a n by k matrix. And so usually you would just declare it as an n by k matrix, and then you could do matrix algebra stuff on it, whereas you can't do matrix algebra on X, but if you index X with like 1, 2, 3 or whatever, then that would be pulling out a vector, and you could do matrix algebra stuff with the underlying vectors that are in the elements of the array X. But you can't just say like X and then multiply it by another matrix. You'll get a syntax error saying, I don't know how to multiply an array and a matrix together. But if you know you want to do matrix algebra with it, you should probably just declare it as an n by k matrix. Conversely, we could get basically the transpose of this by declaring an array named X that is of size n. So it has n elements to that array. Each of those n elements is a row vector of size k. So that's another thing that sort of mentally is basically the same thing as the n by k matrix. Now, previously I said, well, you should never have a real array that's one-dimensional. You should just use a vector. Most of the time, if you're in this sort of thing that, you have something that is explicitly or conceptually a matrix, you should just make it explicitly a matrix. And then if you want to just use it as a holder, you can, and you can access the elements of it and stuff like that. But this array of vectors, array of row vectors does have its uses, not so much in situations where you want to like be doing matrix algebra and stuff on it, but if you need to access the rows or the columns of this sort of conceptual matrix, it can be more efficient to declare and store things this way. The reason why that's the case is if you have something that's explicitly a matrix, the elements are stored in so-called column major order, so top to bottom, left to right. And so if you declare something as literally a matrix, it's slow to access things row-wise because like 7th row, 2nd column, 7th row, 3rd column, those two things are not adjacent to each other in the computer's memory. The 8th row, 2nd column is adjacent to the 7th row, 2nd column, etc. And so if you need to access things column-wise, a matrix is not a bad way to do it. But if you need to access things row-wise, then it can be, let's say, more efficient for you to declare this as an array of size n. So you have n rows, so to speak, each of which is a row vector of size k. And then if you need to access the whole thing for observation number 7, you can just do x bracket 7, and now you have a row vector of things that are in contiguous memory. So that's a little bit of a technical point. If in doubt, just use a matrix. But there are some uses for arrays of vectors, even though those uses do not include linear algebra functionality on the whole thing, only on the individual list elements. Also, vectors and matrices, because they're implicitly real, they cannot contain genuinely integer data. And so if you need to do so, use integer arrays. Those make sense. Those can be of 1 dimension, 2 dimension, however many dimensions, and these are declared like this: ny of size n, int y, size n, or first dimension n, second dimension p. This is basically declaring an integer array in 2 dimensions that has n rows and p columns, and you can then access the individual elements of y, or by row, by column, etc. You just can't do matrix algebra on those either. Rashika. Yes. Right. So if you have like a design matrix, a matrix of predictors, some of those can be dummy variables, like, and it has ones and zeros or whatever. They'll just be stored as double precision numbers, even though it's like 0.0. And there's nothing really wrong with that. In fact, if you're going to be multiplying x by a vector of coefficients beta, that's a really efficient way of doing things. Where this comes into play is more on outcome variables, where Stan is going to be very strict about the types, because it needs to know, okay, is this outcome variable like integers that are 0 or 1? If you're trying to pass it to like Bernoulli logit function, are these counts? You're trying to pass it to a Poisson. And so even if you have thing counts, but they're stored as real numbers, so it's like 10.0, and then you try to give that to like the Poisson probability mass function, you'll get an error saying, you know, left-hand side variable has to be integers, not real numbers, even though your real numbers didn't have any decimal places. So Stan is going to be more strict about the types of things that can go into this or that function in a lot of situations. And so if you have a count, you should store it as an integer, not so much because it takes up less memory, because it's necessary in order to get past the parser errors that would otherwise occur. Questions about that so far? I think I mentioned this before, but the RStan package has a lookup function named lookup, in which case you can input the name of an R function, and it will try to find the most analogous Stan function for you, or you can input a regular expression, in which case it will try to find, or it will find all matching Stan functions. And so if you load up the RStan package and you want it to find all functions that start with env, should not have a $sign there, start with INV, but do not end with G or F, then you could pass like this regular expression, and you get back things like the inverse chi-square distribution, the inverse of a matrix, inverse gamma distribution, inverse logit function, inverse phi function, inverse square root, etc. All the functions that start with INV. So you can, this is basically just a digitization of the index in the Stan user manual, which is a very good, albeit 600-page user manual, but it can be a lot faster to look up things through the lookup function than to look them up in the index. However, if you do look them up in the lookup function, it will tell you the page of the Stan manual corresponding to the version of RStan that you are using. So it is important to always keep your RStan package up to date. Otherwise, the page numbers of the 600-page and growing user manual may not correspond to what you see on your screen if your RStan is old. So yeah, you can use that to find the functions that you think you need to be calling in Stan. Okay, so a Stan program, and by Stan program we mean like the file on the disk that has a .stan extension to it, where you've written out all this stuff, consists of a series of blocks. Thus far, at least officially, we've only dealt with the functions block, although some people have been looking ahead and whatnot. But anyway, Stan permits users to define and use their own functions, which we have been using a little bit in the first part of the semester to write functions that draw from a prior predictive distribution or evaluate the sampling distribution of some frequentist estimator, etc. So we have some familiarity with this already. If you're going to do those, you have to define them in a functions block as opposed to just like anywhere you want. Has to be in the functions block, and the functions block has to come first. So thus far we've only done the functions block. There's some more blocks that come later, which we'll talk about the rest of the day. These user-defined functions, you cannot evaluate or validate those constraints at compile time or even at runtime. If you're going to do that, it has to be inside the functions, but you can put print or reject statements inside those functions if you get input that you were not expecting. These user-defined functions in the Stan language are very useful for many reasons. It's easier to reuse them across different Stan programs. There's actually a mechanism where you can just say pound include and then give it another file name. And so if you just have like a big file that has all the Stan functions that you use, you can just be including that in another Stan program every time you need those. And so you don't have to be always rewriting and copying and pasting, making a bunch of errors like that. It makes the subsequent chunks of code more readable in your Stan program when you're calling these user-defined functions, particularly when the function that you're doing is, kind of on the long side, but it's not doing anything particularly complicated. You don't want to distract yourself or the readers of your code with stuff like that. Just wrap it up in a function, and then when you're seeing it later in your Stan program, it's just one line in there. Enables you to do posterior distributions that involve ordinary differential equations, systems of algebraic equations, numerical integrals, etc. All of these you have to first define your user-defined Stan program that characterizes the system of equations or whatever that you're trying to solve in order to use that system solution to the system of equations in a Stan program, and to be able to get the posterior distribution of the parameters that go into that. We've seen already they can be exported into R via the exposed Stan functions in the RStan package, which allows you to check that your functions are working correctly. And so there's really no excuse for having mistakes in a function like that, because you can easily check it on the outside. And so you should really be using a user-defined Stan function when you're doing anything that's like non-trivial, that you can't just like look at and immediately see, oh, this is correct. And so if you're adding two numbers together, you don't need to make a Stan function to do that. But if you're doing something even moderately complicated, it's best to wrap it in a function. Functions in the Stan language, regardless of whether it's your own or the built-in ones, have to be called by argument position rather than by argument name. This is one of the things that makes them different from R, but that's the way it is in C++. Moreover, for the vast majority of functions that are built or built in or your own, there are no default arguments. And so you have to literally spell out every argument to every function. But when you're making your own functions, they cannot have the same name as an existing function, or they can't have the same name as a keyword in Stan. But they are case sensitive, so you can use just capitalize it to avoid the name conflict, etc. Again, I think I said it before, but you can't have spaces in symbol names. You cannot have periods in symbol names in Stan. That's another difference from R. And so if you're tempted to use a period, you should probably just use an underscore, but you should probably be doing that in your R code as well. Questions about the functions block? No, I've seen that already. Outside of the functions block, any primitive object can have lower or upper bounds. So if you're sort of declaring K as being the number of columns of some matrix, you can declare it with a lower bound of 1. And if that condition gets violated, then you'll get an error message. And so that's a good way to prevent yourself from making mistakes. You know, real numbers, they could have, or anything can have both lower bounds or upper bounds. In the case of both real numbers and integer numbers, the bounds are considered to be like square bracket bounds. So 1 is legal, and like -1 is legal if you're specifying the bounds on k or row. You can do the same thing for a vector. So lower bound of 0. That means all k elements in the vector alpha will have, or are expected to have, a lower bound of 0. Same thing for a matrix. There are some specializations to vectors. These don't correspond to row vectors. That's one of the reasons why a vector and a row vector are different things in Stan. The vectors, which is to say column vectors, can be further specialized, not to have arbitrary bounds, but to satisfy some other conditions. So the unit vector is a special type of vector, but it's still a vector, so we declare it with size k. And a unit vector is one whose sum of squares is fixed to 1. So we've seen those maybe a couple times or last semester. So you can, if you need to, you can declare a unit vector. Similarly, you can declare a simplex vector of size k. This is going to imply the inequality constraint that all the elements of x are non-negative, and the multivariate equality exact restriction that they sum up to 1. So a simplex vector is basically a representation of a PMF. You can have ordered. So ordered is implicitly a vector. There's no like underscore vector after that. But you can declare an ordered vector of size k. That is going to imply inequality restrictions that each element is bigger than the previous one. And positive underscore ordered of size k is the same thing as ordered, but it implies the first one, and consequently all of the subsequent ones are also greater than 0. So you can use those if necessary. These specializations, you can't have like lower and upper beyond what's already implied by this. So you can't have like positive ordered and have an upper bound on that. But positive order implies that they're positive and they're ordered. Questions about positivity, orderness, or vectors? Similar deal with a matrix. These have some specializations. Cove underscore matrix to declare this only has 1 index because cove matrices are necessarily square. Sigma, and that sigma is implicitly going to satisfy the positive definiteness restriction and thus be admissible to be a covariance matrix. It is typically better to use Cholesky factors of covariance matrices that can be called with the keyword Cholesky underscore factor underscore cove. And then analogously with the correlation matrices, and a lot of times it's better to use a correlation matrix and a vector of standard deviations than just a plain covariance matrix. But core matrix of size k or Cholesky factor core to do the Cholesky factor of a correlation matrix. The correlation matrix will not only be positive definite, but the diagonal elements of it will be fixed to 1. And of course, both of these are symmetric. If you declare one of the Cholesky factor things, it's going to be lower triangular. Remember, R does this ridiculous thing where its Cholesky factors are upper triangular. There's a very small subset of statistics who just looks at everything backwards. But the linear algebra people, like Cholesky factors, are pretty universally lower triangular, and that's the way they are in Stan. A lot of the matrix stuff that is in Stan is more influenced by MATLAB than by R. So yeah, they do things that way. Becca.
So in all of our past work, we put these kinds of things in the function because we want the function.
Yeah.
Is that what you would normally do, or do you normally out?
Right. So only in the functions block is it like that. The other blocks, which we're about to talk about, they're kind of just floating.
And does it evaluate things like in R, where you can't do the function unless the stuff is previously in the file bin?
Correct. So if you have a function that calls another function, so you wrote two functions and the second one calls the first actually has to be defined higher up in the functions block. Yeah. So C++ like R, things are evaluated from top to bottom, and you will get an error message from the parser if you're trying to use something that has not already been declared. You will not get an error from the parser if you try to use something that has been declared, but you haven't defined it by filling in the stuff. So, I mean, you know, if you just declare a matrix, it's going to have NAs in it. And so subsequent stuff's not going to work too good. So before we jump into writing a stand program, I want to go back to thinking about simple, not quite as simple as the PMF we used in week 2. When thinking about bowling, it was based on these ratios of Fibonacci numbers. That had to be as simple as it was at the time because that PMF didn't have any unknown parameters to it. All it took in was like the number of pins that are still standing, and you know, output the probability of knocking down X pins. And that's because parameters are typically continuous, but you typically start learning about probability with discrete random variables, so the pins rather than the probabilities, you know, some parameter representing how probability they're going to be knocked down. After we learned about, you know, continuous random variables and vectors and stuff, we could easily write down a somewhat more realistic model for a data generating process like bowling. And a slightly more complicated one would be something like this, where we have a simplex pi that is of size 11 corresponding to, you know, knocking down 0 pins, 1 pin, 7 pins, 10 pins, etc. So that's going to be of size 11 because there's 11 things that could happen on the first roll of a frame of bowling, but we know that one of them has to happen. And so the elements of pi, they're not only non-negative, but they have to sum up to 1. Again, remember, Stan, like R, starts numbering at 1. This is actually unlike the underlying C++ and Python and some other languages that start numbering at 0, but Stan starts numbering at 1. So the first element of pi corresponds to the probability of knocking down 0 pins on the first roll of a frame of bowling or rolling a gutter ball. Anyway, we have a simplex vector pi of size 11, and in a generative model, we can describe our beliefs about pi, or at least we could if I could correctly pronounce whatever distribution this is. But I do know that the distribution is defined for simplex vectors, and it takes a vector of size 11 alpha, which is basically the shape parameters of the distribution. Those have to be positive. They don't have to add up to 1. They just have to be positive. And then we saw before about like the expectation and the variance and stuff depend on the alpha vector that you pass. Certainly, it's very common to just make alpha equal to some positive scalar multiplied by a vector of 1s. So you're really using the same shape parameter for all of them. That will yield a so-called symmetric distribution. And if alpha is all 1s, then all simplex vectors are equally probable, subject to the constraint that they're non-negative and they add up to 1. So we described our beliefs about the unknown pi. Then the next step in the generative process is to say, well, what happens on the first roll of a frame of bowling, and we can think of that as being a draw from a categorical distribution. So one of the 11 possible things is going to happen, and the probability of each of those things is given by the simplex vector pi. After the first roll happens, then we can draw x2 from a categorical distribution. But what the probability of this or that thing happening on the second roll depends on what happens on the first roll. And so if pi, adds up to 1 and you knock down, let's say, 8 pins on the first roll, there's only 2 pins left standing. Consequently, there's only 3 things that could happen. You could not knock down any pins on the second roll, you could knock down 1, or you could knock down 2. And so we need to supply in this last line here a different simplex vector, but we're just going to do a renormalization of our original simplex vector pi. And so we're going to take the elements of pi from 0 up to 10 minus x1, which is the number of pins remaining. Since pi sums to 1, the sum of the subset of the first, several elements of pi is going to add up to something less than 1. So consequently, we divide by 1 minus, that should be starting from 10 and going back, the probability of the left out elements of pi added together, and then we divide that by 1 minus that sum. We now have a shorter simplex vector, but it's non-negative and adds up to 1, and so it's suitable for use on the second roll of a frame of bowling. Robert?
So this model does not account for it being harder to knock down each paper.
It's still simple. It's just not quite as simple as what we were doing when we knew a whole lot less than we know now. Hopefully. Other questions? Anyway, so this is sort of the math representation modulo a typo here and which way we do the sum of prior predictive distribution. And we could do this for multiple frames. Anyway, we draw the unknown parameters from a prior distribution. We draw the data from the data distribution. In this case, it's a marginal and a conditional. And then if we had multiple frames, we would repeat these 2 steps for the number of frames we have. We would end up with these realizations of x1 and x2, or x1, x2, and pi. And we'd be like, okay, we can evaluate whether our prior makes sense. Does the sort of simulated frames of bowling that we get look like we anticipate real frames of bowling to be? Anyway, that's drawing from the prior predictive distribution. When you have data, that is going to be a little bit different. So prior predictive distribution entails drawing from random number generators, but you're just sort of specifying the distribution that you want to do a random draw from. When you have the data already that you believe to be the output of a process like this, you're just not entirely sure what pi is. Now you're drawing from the posterior distribution, and drawing from a posterior distribution requires that you first write down the kernel of Bayes' rule in log units, and that defines the distribution that doesn't really have a name that Stan is going to be drawing from with the nuts algorithm. So yes, we have a prior distribution that we may not be able to pronounce, but it has a name. But the conditional distribution of pi, given the data, does not have a name in this data generating process. And so we have to define the kernel, the numerator of Bayes' rule, but in log units, so the product becomes a sum of logarithms in order for Stan to know what distribution it needs to be drawing from to make that topology and then to move randomly around that space. Stephanie?
If you have the data already, you just draw from the prior to see if you're on the right track, right?
Yeah. So ostensibly, you could even do this before you've even collected the data. But if you have you know, some data, or you just know what bowling data is like supposed to look like, then, you know, you can see if your priors make sense, basically, with the prior predictive distribution. Once you've done that and you have wild data that you've collected, then you want to be drawing from the posterior distribution. But because that doesn't have a name, we have to characterize it with the numerator of Bayes' rule in order for Stan to be able to draw from that distribution. And again, Stan, the draws are not totally independent, but they're pretty close a lot of the time. And so we can make inferences about that. So to start in with the other blocks, the data block comes after the functions block. The functions block can be empty if you don't have any functions, or you can just skip it. But you pretty much always are going to have a data block because it contains all the exogenous and the endogenous knowns. And these things that you declare in the data block are going to be passed from R to Stan as a named list on the R side. So you have to make yourself a list in R that has names, and the names need to correspond to the same names as you give things in the Stan program. And then we'll see a little bit later that you can pass that list of data to Stan, and Stan is expecting that list. The elements can be in any order, but the names correspond to the names of the things that you declare in the data block. Those could be, you know, the outcome or the endogenous known Y. They can be predictors, you know, a matrix X. They can be constants like N or K that are integers, or they could be hyperparameters that go into your priors when defining the numerator of Bayes' rule, in this case, alpha. So basically everything in the data block is everything that the posterior distribution is going to condition on in order to get the posterior distribution of the unknowns, which we'll talk about in a second. Anywhere this applies to functions as well, you can have comments. Those should be in C++ style with either the double slash, or you can have a multi-line comment if you contain it within slash star things. Like C++, white space is essentially going to be irrelevant, except you should have white space after keywords. So having a space here is critical because it needs to know, okay, I'm ending after the angle bracket. Sebastian.
Is there a similar style guide as with R in terms of like space?
Yeah, a lot of the, you know, it's not super strict, and we have more strict style on the underlying C++. But yeah, if you look in the Stan manual, there's some guidelines on that. Basically, if you just do what RStudio encourages you to do with the highlighting and, you know, things like that, it'll be in pretty good style. It's not nearly as strict as like Python or something like that. So an example of a data block, albeit a short one, would be, okay, here we have an integer array. These are going to have a lower bound of 0. And this is going to be my table. It's 11 by 11 of how many times a person knocked down this number of pins on the first roll, this number of pins on the second roll of a frame of bowling. And so this is really going to contain counts. If, you know, the person does like 50 frames, you know, how many times did it go 7 on the first roll and then 3 on the second? So maybe that happened like 4 times. And so you'd have 4 in that cell of the table. Obviously, the ones in the top right are just going to be all zeros because those are impossible. But, you know, the ones on the diagonal or below the diagonal, they're going to have counts. But obviously, those are going to have a lower bound of 0. Also, in the model that I was talking about, I need a vector that is non-negative of shape parameters that is going to go into my prior for the unknown pi. But anyway, I'm conditioning on the data, and I'm conditioning on my prior beliefs about pi to obtain the posterior distribution that we're going to build to. Becca.
Right. Table data type?
No.
Calling it
Table is the name I gave.
called a table.
It is 11 by 11
Table.
table. Yes, Ju.
So I don't understand like values that would be.
Right. So those are counts. So imagine you did like 50 frames of bowling. The count of the number of strikes would be in the bottom left. The number of times you get 10 and then 0 implicitly. So that could happen like 12 times out of 50, maybe. And then, you know, the number of times you do like 0 and then 3. That would be, you know, top row, fourth column, etc. So anyway, the number of occurrences of that event. Please.
I also don't understand the syntax of the table, like the line table, because to me it seems like once the line below, like it's vector and it's a vector of size 11, and there are 11 elements. But
Yes.
then the line above is like an integer, and there's like no size defined because I guess that's fine for integer. But like table, where is it defined? Is it defined in R before, or is it?
Right.
Say like that's a matrix.
Yes. So it's not a matrix in the strict sense. It's, you should more think integer array. But in R, you would make an 11 by 11 integer array named table that has these counts. The reason why, in this case, the brackets come after, that indicates array. Whereas in this case, vector, it comes before. That is for single vectors, single matrices, etc. So that was, yeah, like this. So array dimensions, like the number of elements, those are post the name of the symbol, whereas sizes of primitive things are pre the name of the symbol. They're attached to the keyword that goes with that object type. We'll see how to pass this at the end if we get there today. But yes, you're going to need a list in R that's named table and named alpha. And alpha should be a vector of size 11. And table should be 11 by 11 integer array that contains counts of those occurrences. After the data blocks comes the transform data block. This is more optional, and you could leave it blank or totally omit it. This is executed only once before all the iterations start, and it's used to calculate deterministic functions of the things in the data block. The transform data block is not really necessary if you're calling stan from R, because you could just do all that stuff in R and pass it into the data block and not use the transform data block. However, stan can be called by programs that are not R. It can even just be called from like the shell on a Linux server. And so your outside program that you're calling it from may not have the functionality you need to do all the transformations and stuff that you might want to do. And so you can do it in the transform data block of stan program. I often use it to check that my data was passed correctly from R by putting like print statements and stuff like that in there. You need to declare those objects before you can assign to them. So this is basically the same as when you're writing a stan function. And any declarations must come directly after the opening curly brace. So here I'm going to define an integer array of size 11 that is going to count up the number of times that this or that thing happens on the first roll. So that's going to have a lower bound of 0. These things, lower bounds in data block and transform data, those are just used to check after the fact that you didn't make a mistake. So stan has like no ability to like guess what you mean or anything like that. But if you say, okay, this has a lower bound of 0, and you accidentally put some like negative numbers in there, stan will catch that later. Anyway, so I declare it as an integer array of size 11. Initially, it's blank, and then I'm going to loop from 1 to 11. and put in there the sum of the elements in the corresponding row, you could say, of table. And so you can index this like a list in R, or you can index, you could have like a comma and then blank to index it like a matrix. Either of those syntaxes are acceptable, but it basically summing up what happens on each row, and that gives you the number of times that this number of pins was knocked down on the first roll of your frame of bowling. And we're going to use first roll in addition to table for some of the subsequent calculations. So we've basically collapsed table, which is a two-dimensional integer array, into a one-dimensional integer array for the first roll. Okay, next block, pretty much required. It's the parameters block of a STAN program, where you declare the exogenous unknowns, whose posterior distribution is sought, and the things that you should have prior beliefs about. The parameters block, like the data block, doesn't have any assignments in it. So you can't be using the equal sign for anything. You can just declare names and sizes and restrictions and stuff like that. But you can't declare any integer parameters for reasons we talked about previously. Hamiltonian Monte Carlo not defined for those. When declaring parameters, you have to declare what the parameter space is. But if you omit the lower or upper bounds, those are implicitly going to be negative or positive infinity, respectively. If you do declare bounds, or like implicitly, like by saying this is a simplex, that means the numbers are going to be non-negative and add up to 1. STAN is doing a change of variables from the unconstrained space that it's actually doing the sampling on to the constrained parameter space that you're declaring in the parameters block. And so you might think, okay, well, there has to be some sort of change of variables like absolute value derivative, Jacobian determinant, something like that. But actually for these transformations that occur behind the scenes to make the things in the parameters block, STAN knows those transformations are occurring, and it does the Jacobian determinant thing automatically for you. So you don't have to do it yourself, but you have to be aware that STAN is basically drawing from this unconstrained parameter space in 10 or 11 dimensions in this case, and then doing transformations of that in order to get a vector of numbers of size 11 that's non-negative and adds up to 1. And so the transformation that enforces that restrictions on pi involves some change of variable stuff, but that's the sort of thing STAN can automatically handle for you. And so you don't, outside of this, if you're doing transformations and you're putting priors on transform parameters and whatnot, you have to do the change of variables Jacobian adjustment yourself. But there's not that many situations in which you're writing down a model where you're going to need to do that. Anyway, in this case, we only have one parameter. It is the simplex vector pi of size 11, and it corresponds to the probability of knocking down 0 up to 10 pins in the corresponding element of pi. After parameters comes another optional block called transform parameters. This is going to be kind of analogous to transform data, or transform parameters is to parameters as transform data is to data. However, the transform parameters block, unlike the transform data block, transform parameter block is executed every time the function is called. So it's going to be executed not only every iteration, but every leapfrog step of the Hamiltonian Monte Carlo thing within each iteration. And so the number of times that the kernel function gets evaluated could easily be like 1,000,000. And the transform parameters block is going to be executed each of those 1,000,000 times. So you don't want to put stuff that you don't need into transform parameters. But if you do need it, then go ahead and declare those objects with a legitimate name and then assign stuff to it the declaration needs to be before the assignment or simultaneous with the assignment. All the declarations have to occur at the top of the transform parameters block. Anyway, transform parameters is one of two places where you can calculate endogenous unknowns. And these sorts of things are deterministic functions of the parameters or things declared in earlier blocks. And so they can depend on the parameters. But, you know, once you get a realization of what the parameters are, you know exactly what deterministic function generates these transform parameters. So you can use the transform parameters block to declare interesting intermediate outputs that go into the log kernel of your posterior distribution. And the reason why I say interesting is because things declared in the transform parameters block are going to be stored in the output because you've said they are interesting. Also, if you declare things with lower bounds or upper bounds or whatever, those constraints are validated. So if you make a mistake in the transformation and you accidentally make something negative that's supposed to be positive, then you'll get an error message rather than just wrong values of that thing. So transform parameters block can be useful. Also, due to the sort of nature of how to do efficient sampling, a lot of times you make what you're really interested in a transform parameter, and you're doing some transformation to make those transform parameters so the things in the parameters block you're not really interested in so much a lot of times by themselves. You're just sort of flipping around transform parameters and parameters in order to get better geometry in your posterior distribution so Stan can sample from it more efficiently with less autocorrelation and stuff like that. We'll talk more about these transformations, not today, but really the rest of the semester. After transform parameters comes a pretty much required block called model. You can also declare endogenous unknowns inside the model block, up at the top, and assign things to them and use them in subsequent lines. But you can't put constraints on declarations in the model block, and things that are declared in the model block are not stored. And so this would be a good place to declare and define things that go into your posterior kernel, but are not interesting. Like if you make eta as like x times beta, that is not a particularly interesting function, and you wouldn't want to like save all n values of eta usually because it's not that important and n could be large, and so you have to store a lot of things. So uninteresting endogenous unknowns you can declare at the top of the model block. They won't be stored, and you can't validate any constraints because you can't put constraints on them. So just make sure you're doing those transformations correctly, and you can use a user-defined function to do so that you're calling in the model block. Anyway, the essence of the model block is it needs to define something, or at least something within a constant of the posterior kernel, the numerator of Bayes' rule, possibly ignoring anything that's a constant. And that is assigned to this variable called target, which initially is initialized to 0, and you keep adding pieces to it. Remember, we're dealing with log units here, and so all the contributions to the log kernel are additive. So remember, the logarithm of a product is equal to the sum of the logarithms. So in this case here, we would be adding, approximately 2 pieces to target: the logarithm of our prior PDF on theta and the logarithm of the likelihood. Those get added, and so you can increment the log kernel by doing target plus equal, and then the priors or your likelihood, whatever you may need for that. There's a ton of functions in Stan that implement these distributions. The ones that end in _ LPDF or LPMF, those stands for log probability density function or log probability mass function, respectively. These for continuous random variables, these for discrete random variables. Those return scalars, even if some of the arguments to them are vectors or one-dimensional arrays, in which case these functions are going to be summing the logarithm of the density or the mass over the elements of the vectors that you supply to them, presuming them to be conditionally independent. And so if you have a statement like this, target plus equal normal underscore LPDF, beta, vertical bar, 0, 1, that's saying you have independent normal priors on the k elements of beta, and not only normal, but standard normal. And it's just going to do like the logarithm of the normal distribution for the first element of beta plus the logarithm of the normal PDF for the second element of beta, summed up over all k elements, assuming under your prior those are conditionally independent of each other. And you've put in the parameters, not in this particular model for bowling, but for like more of a regression model, the vector is, beta is an unknown vector of size k, and this encodes its prior. Or you can use your own functions if Stan doesn't have the distribution that you need, or you can just put like target plus equal 42. You can just have an expression that you're adding to. Of course, adding the constant 42 isn't going to change anything, but you know, if you had your own distributions or something like that. So in the case of bowling, here's an example of a model block. So first, and when doing this model block, it's good to think about this, okay, from the perspective, which may not be totally true, but you're writing this before you actually observe what the values of the data are. So you can think of these as sort of pre-data probabilities. So increase target by the multinomial PDF for what happens in the first roll, given pi. Then if someone gets a gutter ball on their first roll, then there's another target plus equal multinomial LPDF for the first row of table, which corresponds to the second roll when the first roll of that frame is a gutter ball. So we have another multinomial statement, but we still have 10 pins standing, and so pi is the appropriate thing to use there. Then we need to loop through to account for the pre-data probability of what happens on the second roll, given that you knock down more than 0 pins on the first roll. So we just loop from 1 to 9. The number of elements to keep is 11 minus x1. We do what we did before in math, where we keep the first however many elements of pi and then divide by the sum of the remaining elements to renormalize it so that pi 2 is also a simplex vector, even though I can't declare it as a simplex vector in the model block because you're not allowed to do things that have constraints on them. Then the number of pins minus 1 is the first keep elements of the table corresponding to the number of pins knocked down on the first roll of a frame of bowling. So this is basically number of pins left minus 1. We have another multinomial increment for these two subsets given pi 2. If x1 is a strike, then x2 is 0 by construction, and so there's no reason to do target plus equal log of 1, which is just going to be a constant, not going to change anything. And then finally, we have our prior on the parameter that we declared in the parameters block, pi, because the logarithm of the numerator base rule just results in the sum of a bunch of logarithms. These are commutative, and so it doesn't matter what order you increment target with. It just matters that you have, you know, all the probability statements that you need that correspond to the numerator of Bayes' rule. Running out of time a little bit, so I'm not going to talk today about generated quantities. We'll talk about that Thursday. but I use it to come up with the posterior distribution or posterior predictive distribution for your score of a whole game of bowling, 10 frames. And we'll go through that on Thursday. So we just generate some data like we did on the first or second week using actually this Fibonacci probability mass function to generate the data. But let's say we don't know that it's a Fibonacci based thing, and we're just estimating our simplex vector pi. We make with a loop this table of the number of times that you knock down, you know, this or that number of pins on the first roll, the second roll, etc. So we can pass it to Stan. We call the Stan function in the RStan package. We give it the name of our Stan program that's defined all the things that I said previously. It's also on Canvas, just as its whole text file. The data argument is a named list. So table is this thing I created with the double loop. Alpha, I'm just going to say, is 1 for all 11 elements. That's going to be sufficient with the default arguments. The default arguments for adapt delta are 0.8 and 10 for max tree depth. You don't need to change those in this case, but in some situations you will if you get a warning message back. That will take a second to compile, or more than a second, more like 30 seconds, like it does with BRM, because it has to translate that to C++, then compile it. The sampling really only takes a few seconds once that happens, and then you can print the output, specify the number of digits you want, etc., and you get all this stuff here. But again, it doesn't really say what pi corresponds to, or even that pi 5 is actually the probability of knocking down 4 pins, or anything useful like that, like Stan or RStan ARM and BRMS does. But you can see we recover, at least in the posterior means, the same sort of increasing sequence of probabilities that we saw like week 2 when we're using this Fibonacci mechanism to define the probabilities of knocking down all these number of pins. The number of effective samples is like greater than 4,000 for all these ones here. It's a bit less for 0, 1, and 2, just because there's like no occurrences in this small data set that I created where the person gets 0, 1, or 2 pins on their first roll. And so there's less information here about these. Consequently, the effective sample size on those margins a little bit less efficient, but still like totally good if you wanted to make conclusions from a model like this. So we'll pick it up Thursday. We'll talk about generated quantities, talk about more about transformations. We'll talk about doing, you know, regression models and stuff with Stan, and then keep going from there. Also, we'll talk about the homework on Thursday.